That's so nice of you. It's nice to see you twice in one day. I hope we can have like an intimate little class, although it's still going to be a lecture class because that's how this class is supposed to be. There are 15 of us. 15 of you, one of me. Okay, ready? Okay, let's go. Okay, so happy Valentine's Day. Today, because it's Valentine's Day, I thought we should do mathematicians who are married to each other. So our mathematician spotlight is Ron Buckmire. This guy, it's kind of hard to see, huh? Let me turn some of the lights off. There, okay. Ron Buckmire and Dean Elzinga, who are married to each other. They both have PhDs in math. So Dean, who's the one on the screen, has a PhD in logic from UCLA, and Ron has a PhD in I forget. From Rensselaer Polytechnic Institute, and they met when they were graduate students, and eventually got married. Ah, so cute! This is the biggest picture I could find that they were both in, and so you might ask, like, well, what are they doing now? So most of the mathematicians that I've told you about have been math professors. So I just told you about what they were doing research in. But interestingly, these guys, neither of them is currently a math professor. So Ron Buckmire is a program officer for the NSF. So he decides, so the NSF is the National Science Foundation. It's the major funding agency for mathematics. And he decides which undergraduate programs the NSF should fund. So for instance, summer programs where you can do summer research, or sending undergraduate students to conferences, that sort of thing. That's pretty cool. On the other hand, so that's this guy, NSF program officer. And then Dean, this guy, got his PhD in logic at UCLA and then was an opera singer. So he was an opera singer for 20 years. And then he stopped his opera singer career and is now a senior machine learning engineer and has done that for a couple of years. Yeah, pretty good, right? So these are career options for you. Good. Happy Valentine's Day. Fall in love, become a mathematician, and then do whatever you want. That is the moral of the story. Okay, so I'll leave, I don't know, which picture do you want? Which picture do you like the best? Oh, this one? Okay, I'll leave, whatever. I'm going to leave it up because we're going to look at some graphs. So we'll just leave something up. Okay. Okay, so the last time we were together, I was losing my voice, but look, it's back. It's amazing. And we talked about the gradient. So now we're just going to look at the gradient and do some more things with it. So it's kind of great. So last time, we defined the gradient of a function is a box of numbers, the partial derivative with respect to x, and the partial derivative with respect to y. It's just a vector made of those two things. And in general, if you have a function of 3 variables or something, I call it gradient of f. And the gradient of f as a function of 3 variables would be partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. Oops. The whole point of that was it was three variables. And so on. So you could have it of as many functions as you want. And then the last time we talked about the directional derivative. And that you have to specify more things. So of a function, let's say of 2 variables, at some point, x naught, y naught, in the direction of a unit vector, u, is the notation for it is the derivative in the direction of u of f, evaluated at the point x naught, y naught. And the way you compute it is you take the gradient of f, you evaluate it at x naught, y naught, and you dot it with u. So that's what you do. Okay, so what we'll do today is talk about, basically, like we mentioned briefly that the gradient is perpendicular to the level curves, but it was sort of like a little side note. And now we're just going to go into that. The gradient is perpendicular to the level curves, and gosh, that turns out to be really useful. So the gradient is perpendicular to the level curves or surfaces of a given function, which we can use to find tangent plane, the tangent plane equation. We can use it to find the tangent plane equation or the tangent line equation. So plane or line. So amazing. Okay, so before we do that though, let's do more familiar territory. So here's what we want to do. I'll write the question down here so we have lots of space for the answer. So let's let f of xy be xy. Secretly, this is like the same function as x squared minus y squared, but rotated, but it'll just be a little bit different. So we have two quests. One, find the direction of steepest ascent, or the direction of greatest increase of the function at the point 2, 1. Okay, so if you're standing at 2, 1, you want to know which way should I go to increase my function most steeply, like maybe most greatly. So maybe you're walking up a hill, you want it to get higher, or maybe it's a temperature function and you're quite cold and you'd like to get warmer most quickly, something like that. Okay, now once we've done that, we want to find the direction. You could go to increase your function value at half this rate. Because of course, you might want to know which way should I go to increase the most, to decrease the most, to not increase at all, or decrease at all, to not change at all. But what if I want to increase but just a little bit? We want to know that direction also. That's the dream. Okay, so let's do it. I have an illustrative picture, but I forgot to pull it up. Okay, my illustrative picture is of snowshoeing in the woods last winter. If you've ever hiked, you might notice that a hiking trail, it doesn't take the path of steepest ascent, right? It doesn't go straight up the mountain. On the other hand, it also doesn't go flat. It increases gradually, maybe at a rate of half as much as the mountain. So if perhaps we are a trail constructor and we wish to define the direction at which you ascend half as steeply as the steepest. Okay, so let's do this. So first, to find the direction of steepest ascent, oops, not direction of steepest ascent. Do you remember what we do to find the direction of steepest ascent? Yeah?
It's the same direction.
Yeah.
It's the same direction as the gradient. Yeah, is that what you're going to say too? Yeah, it's the direction of gradient. Okay, so we have our function, f of xy equals x times y. So let's compute the gradient of f is a function of x and y. So derivative with respect to x, derivative with respect to y. Can you, I think I had this as a column vector. Can you do it? Derivative with respect to x of x times y? Y. And then derivative with respect to y is x. So if, let's see, we're interested at the point 2, 1. So the gradient of f evaluated at 2, 1 then would be 1, 2. Nice. 1, 2. Okay, great. Okay, and now, okay, fine. So if I walk in the direction of the vector 1, 2, it's going to be the steepest rate of increase. Can you say what the slope is going to be, what the directional derivative is in that direction? Oh. can you say again? I didn't quite hear how you got that.
It's just magnitude. Just do 1 squared plus 2 squared and square root of that.
Yeah, exactly. The magnitude of the gradient. Yeah, exactly. Magnitude of the gradient. So square root of 1 squared plus 2 squared, root 5. Nice. Okay, so if we walk in this direction, our slope will be very steep, square root of 5. Okay? Great. But we're not quite interested in such an extremely steep hike today. We want to go half that. So direction to climb or increase your function at half this maximum rate of increase. Well, let's see. We want to find, let's see. We know that the amount, the rate of increase, is the directional derivative of u f at 1, 2, no, 2, 1, which is just the gradient of f at 2, 1 dot vector u, which is, since this is the dot product, the gradient of f at 2, 1 times the magnitude of vector u times cosine of theta. And because vector u is a unit vector, this is just the magnitude of the gradient of f at 2, 1 times cosine of theta, where, okay, your gradient vector is 1, 2, which is something like this. And then your unit vector, well, it's, I don't know, we have to decide which way it should go. But okay, so this is the directional derivative. And our goal is we want this to be half of the maximum. So we want this to be half of the magnitude of the gradient of f at 2, 1. That's what we want. So how would you do it? Yeah, Ricardo?
Find the theta that gives you 1/2.
Yeah, exactly. Yeah, nice. Because find the theta that gives you 1/2. Because this part is the same, and this part is the same. So it just tells you that cosine theta has to be 1/2. Nice. And if cosine theta is 1/2, then theta is pi over 3 or negative pi over 3.
Just to clarify, why is it the magnitude of u is supposed to be equal to 1?
The magnitude of u is equal to 1 because u is a unit vector. And that is because we want to know, when we want directional derivative, it's like you want how much your altitude is changing per how much your horizontal is changing. So if I step 1 foot in the horizontal direction, how many feet does my z value change by? So you take a unit direction vector. Okay, so if this 1, 2 is our gradient, we want, okay, well, we could have gone in the perpendicular direction and then nothing would have changed. Our height wouldn't have changed. But we want to go negative pi over 3 or positive pi over 3. We want to rotate our vector by negative pi over 3 or by positive pi over 3. Those are not the most equal angles I've ever drawn. Let's try again. Maybe that's better. Okay, so we want to take our 1, 2 vector and rotate it. I could have made it so it was really nice, but I thought it would be a good idea to review rotation matrices from linear algebra. Always a good opportunity to bring linear algebra back in. Okay. Okay, so our goal then is to rotate our direction vector 1, 2 by pi over 3 and negative pi over 3. So let's first rotate by pi over 3. So we have some rotation matrix times 1, 2. So I think it's cosine, negative sine, sine, cosine is the rotation matrix. I suppose your professor taught you this long, long ago. I see some blank stares, but. So cosine pi over 3, negative sine pi over 3, sine pi over 3, cosine pi over 3. I see so many blank stares that maybe this is the time to review this.
Yes, sorry, just why, I'm just interested in why we're putting in those specific cosines, negative sign, and just where are they coming from?
Yeah, so, okay, so let's say, where does this come from? Where does this matrix come from? So, if you have a matrix, A, B, C, D, notice that when you multiply by 1, 0, you get the first column. And when you multiply A, B, C, D by 0, 1, you get the second column. So a matrix is completely determined by where it sends 1, 0, and 0, 1. So if you know where you want to send 1, 0, and 0, 1, you got your matrix. You just fill them in. This column, first column, is the image of 1, 0, the place where 1, 0 goes. And the second column is the image of 0, 1, the part where 0, 1 goes. Okay? Okay. This is our diversion, our temporary diversion. Okay. So our intermediary goal here is to write a matrix that rotates the entire plane by theta radians counterclockwise. It just rotates by theta. Okay, and so the idea is to figure out where 1, 0 and 0, 1 should go and make these the columns of your matrix. Because if you want to know what the entries of your matrix should be, you just say, where do you want to send 1, 0? Put that in the first column. Where do you want to send 0, 1? Put that as the second column. Now your matrix is done. So let's figure out where 1, 0, and 0, 1 go under a rotation by theta. So here's our unit circle. Here is the vector 1, 0. And now I'm going to rotate it. Okay, I'm going to take this guy and rotate it by theta. Theta is this number. Okay? Okay, and then what I want is its x-coordinate and its y-coordinate. Okay, so in my matrix, this column is where 1, 0 goes if you rotate it by theta radians counterclockwise. Can you figure it out? The x component, if this hypotenuse is 1, do you know what this length is? Yeah? Cosine theta, yeah, it's the adjacent side. And this y component is sine of theta. Okay, so that tells us that this should be cosine of theta, and this should be sine of theta from this triangle here. Okay, good. Well, we just have one more to do. We want to know, where does 0, 1 go? So I'm going to rotate it by the same theta, counterclockwise, and figure out what its, that's also theta, what its x and y should be. Okay, so how long is this piece? It's cosine theta, yeah, because this right triangle here is congruent to this right triangle here. Just move it over. So the short side of this is the same as the short side of this. So if this was cosine theta, this is also cosine theta. If this is theta, this is also theta. And it's positive. So this is cos theta. And then how about this length? It ends here. It's okay. Sine theta, yeah, it's sine theta. And it's going in a negative direction. So its length is sine theta, but its coordinate is negative sine theta. So the x-coordinate is negative sine theta, and the y-coordinate is cos theta. We did this for an angle theta between 0 and pi over 2, but you can try it for the other quadrants, and it also works out. Yeah. Yeah, so this is actually a great trick. If you know where you want to send 1, 0, and 0, 1, you get your whole matrix. It's pretty good. Yeah.
What does it say under the idea? Figure out where.
Figure out where 1, 0, and 0, 1 should go, and make these the columns. So this first column was where 1, 0 goes if you rotate by theta, and this is where 0, 1 goes if you rotate by theta. Yeah. Okay. Are you willing to do it? Or shall we do it? Okay. Okay. So let's recall our vector was 1, 2, and we wanted to rotate by pi over 3 and negative pi over 3. Okay. So let's rotate 1, 2 by pi over 3. So this would be cos pi over 3, reading off of this matrix that we have now so nicely. Cos pi over 3, negative sine pi over 3, sine pi over 3, cos pi over 3. And then we multiply by our 1, 2. So if we turn this into numbers, cosine of pi over 3 is a half. Sine of pi over 3 is root 3 over 2, so negative root 3 over 2. And then root 3 over 2 and a half. Times 1, 2, and then you can multiply that out and get some numbers. And you will be happy. For example, it would come out to 1 minus 2 root 3 over 2, comma 2 plus root 3 over 2. And then the question was, which way should you hike in order to descend half as much as the steepest way? And usually what you want out of that is a unit vector direction. So if you wanted to turn it into a unit vector, well, you could turn your original guy into a unit vector. This 1, 2, not a unit vector. Longer than a unit vector. It has length root 5. We already figured that out. So if you just divide everything by root 5, rotating doesn't change the length. You can just turn it into a unit vector. Okay, and the same thing for rotating 1, 2 by negative pi over 3. You would do exactly the same thing, but with a negative sign inside the angles.
So you said if you just divide all through by root 5, that just makes it a unit vector?
Yes. This makes, yes. Divide by the length to get a unit vector. Yeah. Often you want a unit vector. Yeah. Okay. Yeah, so in the picture, if we're interested in things that are happening at the point 2, 1, we found that the gradient of f at 2, 1 was the vector 1, 2, and that is the direction of steepest ascent. And the slope in this direction, or the rate of change, we found that it was positive root 5. That's the biggest it can possibly be. And then if you want to descend at the steepest rate, you want to go downhill. Do you remember which way you go?
Yeah, just negative.
The negative, exactly. So maybe I should make that red because it's negative. So negative gradient of f at 2, 1. The slope in this direction would be negative root 5. It's the same idea. And then if you suppose you didn't want to increase your direction, increase or decrease at all, you just want to hang out at the same level. Which way do you think you should go? Yeah, perpendicular, exactly. So we go perpendicular. So if you go this way, the slope or directional derivative will be 0. And then we just computed these things. So we didn't do this one, but we could have. Same idea. You would have this direction, this guy rotated by pi over 3, this in this way, or in this way. This would give slope to be a half of root 5.
Why is that slope 0 when you do
The slope is 0.
Well, there's like,
Perpendicular?
yeah.
Yeah.
Why?
Can anybody say, so the question is why is this slope 0, the directional derivative 0, when you go perpendicular to the gradient? Yeah.
The gradient is perpendicular to the level curve, and the level curve is flat.
Yeah, the gradient is perpendicular to the level curve, and the level curve is flat on the surface. Yeah, good idea. Mm-hmm. So that's a geometric way of thinking about it. And if you want it as an algebraic way of thinking about it, you can think of that the gradient of f, no, the directional derivative in the direction u of f is the gradient of f times cosine theta, where theta is the angle between f and the direction that you're going. And if you want this thing to come out to 0, then this better be times 0. So that tells you cosine theta has to be pi over 2 or 3 pi over 2. So if they're going to, like the dot product of two things is 0, maybe that's the way I should have said it. That would be good. OK, the directional derivative is the gradient dot the direction that you're going. And suppose you want it to be 0. You want your slope to be 0. Well, then the dot product of these things had better be 0, so they're perpendicular. Yeah? Yeah, OK. So the gradient is this guy, and our vector u is going to be perpendicular. Yeah. OK. OK. So the next thing to do is I have this nice picture here of some level curves, and I would like you to sketch the gradient vector at each of the points. So I gave you some points to try, then you can draw some more points if you want. So please do that, and then I'll draw it on the board. Go.
I'm making it perpendicular to the level curves.
Can you say some words there?
I looked at the points and I pointed them in the positive direction, perpendicular to the level curves.
Nice. OK, are you willing to take on a challenge now that you're up there?
Sure.
OK, so here's a question. Which direction vector has greater magnitude? The gradient at P, which you've drawn, or the gradient at Q, which you've also drawn?
Q.
OK, Q, that's correct. Why?
Because you know it's steeper since the level curves are more dense, I guess, at that point.
Yeah, nice. OK, are you willing to go back and change your vectors to make them sort of scaled appropriately? So I agree with all your directions, although this one doesn't look quite perpendicular. This is a vertical line. This one doesn't look quite perpendicular. This is a horizontal line. But anyway, that's so nice. So nice. Scale them all appropriately.
Just to clarify, it's just
Perpendicular. Yeah. And then P maybe a little smaller. Yeah. Yeah, so nice. So nice. Thank you. Well done. Great job. Okay. Great. Okay. Great. Okay. So yes, they are perpendicular. Perpendicular to the level curve. I wrote it down incorrectly twice and copied it twice. Perpendicular. Perpendicular to the level curve, of course. Yes, that's what we've been talking about. Okay. Okay. So, good. So, just now we're going to use it for something else. Okay. So, so we want to know maybe why is the gradient perpendicular to the level sets? So, level curves or level surfaces. So one reason is what we said before. So the gradient points in the direction of steepest ascent. and negative gradient of f is the direction of steepest descent. And directly between these is no change. So infinitesimally, wherever you are on your surface, it looks like a flat plane. If one direction is greatest ascent and the other direction is opposite direction is greatest descent, then perpendicular to that will be the direction of no change. So we've been talking about that. And then algebraically, the level set or curve of a function of two variables, f of x, y, at level k, has equation f of x, y equals k. So now we'll do a little bit of algebraic manipulation. So suppose the level curve is given by the equation r of t equals x of t, y of t. Okay, so you're going along the level curve, and you want to take f of it. So f of x of t, y of t, tells you how the function is changing along your level curve, and in fact, it's not changing at all. It's k, because you're on a level curve. So f along your level curve is just k. That defines a level curve. So suppose we take the derivative of both sides. So we take the derivative of this side, and we take the derivative of the other side. Now, I know that the derivative of a constant is 0. It's true. Now, the derivative of the left is slightly more complicated. We have to use the chain rule. It will be partial of f with respect to x times dx dt plus partial of f with respect to y times dy dt. And this will be what we'll use. So let me write that again. That we can recognize that as a dot product. Partial of f with respect to x, comma partial of f with respect to y, dot dx dt, dy dt. Now this guy, I know what it is. That's the gradient. Okay? So this is the gradient of f at x, comma y, or at our point, x naught, y naught. Dot, okay, another way to write this is x prime of t x
Y with that Y. Minus
minus y. Okay, cool. And then
X equals
xy minus x. So the gradient of f at 0, 1 is what? 0? And is it 0, 0? It's negative 1, 0, but okay. Negative 1, 0. Is that what it is? Yes, negative 1. Wait, did anybody compute it? So 1 times 1 minus 1? What am I doing wrong? 0? What? It's 0, 0? Okay, we should pick a different point. Is there a better point? Oh, I see. Maybe 1, 1. Let's pick 1, 1. Let's set it equal to 0 and pick the point 1, 1. Is that going to be better? Yeah. So let's do this at level 0 at the point 1, 1. Okay. So let's do this at the point 1, 1. And then if we do it at the point 1, 1, we should get something else, right? E minus 1, E minus 1, E. Is that right? I don't want to get 0, 0. Life is weird when we get 0, 0. Okay. Okay, let's do it at 1, 1. Good. And now, so that's E minus 1, E minus 1, which is actually some vector that looks very much like this. It's at a 45-degree angle. Okay, so a perpendicular vector to the gradient of f gives our tangent vector.
The question.
Yeah.
I
Is it
think
not?
either the 1 minus 1 isn't 0, and I think that with the point 1, 1, that's not, like, it's not on the curve.
Oh. Okay, what should this be?
E minus 1.
E minus 1? Okay. Good call. Very good call. I agree. But with 0, 1, there was a problem, right? Gradient came out to 0? 0? Okay, so we had to fix it. Okay, so our curve is a level curve at level E minus 1. That's fine. Okay, we have a point, which is 1, 1. And now we have a direction vector. Okay, so we have a perpendicular vector, which is E minus 1, E minus 1. Can you find a tangent vector? Something that's perpendicular to this guy? Yeah, how would you do it? Yeah, flip it.
Yeah, you flip it and you make one negative.
Flip it and make one negative. Okay, so I'm going to flip it. Instead of E minus 1, E minus 1, I'm going to go E minus 1, E minus 1. That's in other order. And then make one of them negative, maybe the first one. So I'll make negative E minus 1. So that gives me 1 minus E, E minus 1. So my line is x of t, y of t equals my point, which is 1, 1, plus my direction, 1 minus E, E minus 1, times t. Okay. Okay. Sorry about the 0 bit there. Yeah.
So what did that last line?
So this last line, this line is the tangent line. So it says, we start at the point 1, 1. We had our gradient vector, which was E minus 1, E minus 1, which went that way. But then we wanted a perpendicular direction, so we chose this one, I guess. Negative, comma, positive. So we chose to go in this direction. And this line says you start at 1, 1, and then you go in the direction 1 minus E, E minus 1 for t amount of time, and t can be any number. So we get this whole tangent line. So this is tangent line to the curve e to the xy minus xy equals 1 at the point 1, 1. And before this, we would not have any way to do that because we cannot solve for y explicitly. But now we can. So great. Okay. Okay, and the last two things, we'll just do it with surfaces. Okay, so the first thing, we'll find an equation for the tangent plane to x squared plus y squared plus z squared equals 3 at the point 1, 1, 1. So, let's see, I do have that one prepared here. So x squared plus y squared plus z squared equals 3. And then I'll put in the point. So we have the point 1, 1, 1. There it is. And I wish to find the tangent plane to this sphere at this point. Notice that you could solve for z as a function of x and y, because you know you're on the top. So take the positive square root, blah, 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 but life would be kind of hard. So let's do it implicitly. So let's consider the sphere as a level surface of the function g of x, y, z equals x squared plus y squared plus z squared at level 3. Okay? So then for the plane, you need a point on the plane. Do we have one? Yep, 1, 1, 1. There it is. And you need a normal vector. Here, life is better, because for a plane we need a normal vector, and that's exactly what the gradient gives us. So we'll just use the gradient of g at 1, 1, 1. So the gradient of g as a function of x, y, and z is 2x, 2y, 2z. So the gradient of g at 1, 1, 1 is 2, 2, 2. And so now our equation, our plane, is like a, b, c dot x minus x naught, y minus y naught, z minus z naught equals 0. So we just say ABC is 2, 2, 2, 2, 2, 2 dot x minus 1, y minus 1, z minus 1 equals 0. And that's our plane equation. So which you can rewrite as 2 times x minus 1 plus 2 times y minus 1 plus 2 times z minus 1 equals 0. And if we plug that in, there it is. Can you see it? Maybe I should turn off the lights again so you can see more. You see how the tangent plane is just barely kissing? Yeah, so nice. If I turn this off, down a little bit. No, maybe you need more. Yeah, if you turn it down, you can see that it's just barely touching the plane there, yeah? So it's the best linear approximation right there. Cute, huh? Okay, for our last thing, we're going to think about the surface x times y times z equals 8, which looks like this. Crazy, huh? It happens in all the quadrants where the product of all three things is positive. So I guess that happens in all the octants, so 4 of the octants. So this is the positive octant where x and y and z are positive, and so on. And our question is going to be, which points on the surface, maybe one, maybe lots, maybe none, are parallel to the plane x plus 2y plus 4z equals 100. That's this plane. We got to zoom out till we can see it. Maybe. Where is it? There it is. Okay, so there's the plane. And we want to figure out which points on the surface are parallel to this plane, have a tangent plane parallel to this plane. How many do you expect that there will be? 4? 3? Hard to know, huh? Yeah, let's see, let's zoom in. Okay, remember which way the tangent plane is going? Now we're going to zoom in so we can see the surface better. Maybe that's a better view. Yeah, well, okay, the answer is going to be that there's only one point. Can you justify to yourself why that could be? Like if these are sort of all facing the wrong way, these are kind of all facing the wrong way, only this is facing the right way for that plane. Yeah, maybe? Okay. Okay, so we'll just do that. So, our next quest is to find all the points on the surface xyz equals 8 with their tangent plane parallel to x plus 2y plus 4z equals 100. Okay? So, parallel to that, so this means, okay, their tangent plane, so tangent plane, it has a normal vector parallel to this plane. It would mean that its normal vector would have to be like 1, 2, 4. So it would have to be 1, 2, 4. Okay, but it wouldn't have to be exactly 1, 2, 4. It could be 2, 4, 8, or 0.1, 0.2, 0.4. So some multiple, like let's call it lambda, some multiple of 1, 2, 4. Okay. So the tangent plane has this normal vector, which tells you that actually the gradient of the level surface function is a multiple of 1, 2, 4. Okay, so let's do it. So we can consider the surface xyz equals 8 to be a level surface of the function h of xyz equals, what should it be? xyz, okay, at level 8. Okay, by the way, you can also do the function xyz minus 8 at level 0. Any of these would be okay. Okay, so we want the gradient of h. Okay, what is the gradient of h? Should be yz, xy, no, xz, xy, to be some multiple of 1, 2, 4. So this gives you 3 equations. It tells you that yz, xz, xy, this one is lambda, this one is 2 lambda, and this one is 4 lambda. And by the way, we also have xyz equals 8. So this is 4 equations and 4 unknowns. So it might have a solution. If you look at, if knowing that xyz equals 8 tells you that x, y, z are all non-zero, because if one